would also like to thank you for the organizer to give me the opportunity to give this talk. So this talk will be about point contact geometry and resistive switching, which we realize in this geometry. So let's see first of all the outline of the talk. So first of all, I will talk about the point contact setup and some details in order to make some terms of definitions. Next, I will go to the actual experimental findings for silver surface. And afterwards, I will jump to quantization effects and histogram techniques which we will use for defining these experimental ID curves which we found in the previous section. And then last but not least, I will conclude my talk. So here we find the drawing of our sample chamber in which we have our setup. So for this device, we use a tool for the tuning of our point contact. The coarse tuning is done by a stepper motor. Here we find the axle of the stepper motor. And what it simply does, it has this cone pushed against the tip holder, and the tip will be pushed against the sample, which is zoomed in here. And the fine-tuning of the contact is achieved by a piezo actuator, which is good because we really able to tune the point contact down to 2 nanometer range. Most of our measurements was done in cryogenic vacuum at 4.2 Kelvin, but we also demonstrated the operation at room temperature. However, the data which I will present will be in cryogenic vacuum at 4.2 Kelvin. So, as I mentioned earlier, we will be able to tune our contact down to 2 nanometer range, which means that we're really able to tune single atomic level, contrast down to a single atomic level, where conductance quantization effects will be important. Now I really don't want to go into the details as I do not really have too much time. I just want to show the Landau arbitrary for this range. It's a classical scale approximation where we will have the conductance quanta, which is 2e squared over h. And from now on I will use denote it as G naught, which is an inverse of resistance as 12.9 kilo ohms. So this is something that it's really easy to measure. So but for now on, what we have is some experimental ID curves. So what we use for measure these curves is we tune the bias voltage on the sample, and we measure the current on the flowing through the sample. And this is one of our experimental findings. We found such curves here. So let me define our environment. So the tip was a chemically etched tungsten wire, which is widely used for STM measurement due to its rigidness and high endurance. And the sample will be simply 100 nanometer of silver evaporated on a silicon substrate. And as I mentioned earlier, this measurement was performed in 4.2 Kelvin cryogenic vacuum. So what we found in this sample is that such an ID curve which is presented here, which is a dipole switching. And what we also found is that, as usual here, is that we have two stable states at zero bias. So this is in some sense it's a non-volatile memory. And usually the threshold voltage for switching was around 0.6 or 0.8 volts. So let's see how can we define this switching. So we have two things that we can define. So we have two slopes at zero bias, providing us the conductance of the on state and the conductance of the off state. And what we have is the difference of these conductances, and also we have the switching ratio, which is the ratio of these two conductance values. And what we have here is that for low resistance contact, for low resistance, I define contacts with really good metallic resistance, which ranges from, let's say, 100 ohm to 1 kilo ohm. So this is what low resistance means here. So what we found is that if we start to tune the maximum bias voltage of the sweeping of the curve, then we will see a smooth variation of the switching ratio, which is visible here, and the corresponding this one. And what we also find is that the on state, I mean the higher conductance states for this case, which is ladder constant over the bias, over the maximum bias. So this leads us the clue that this is an ionic conductance thing, as was mentioned earlier. Sometimes in the literature, these are just two examples for such a thing in the literature, where they have the argument that metallic silver can dissolve back and forth in silver sulfide surface. For our case, we didn't put any silver sulfide on purpose. So I have to stress that most likely this is some sort of surface contamination. And indeed, Rutherford scattering data showed later on that we indeed had sulfur on the surface, although we didn't really have too much data on the profile. So now on, we have similar data as earlier, but what I really want to stress is that, okay, let's go down to lower conductance values. That, okay, let's see how can we statistically analyze such data. First, I would like to define the push-pull histogram for a point contact setup in which we have a sample and we periodically indent and unindent a tip, in which in our case it's a tungsten tip in the sample. And what we will see that is we have this displacement of the sample over time, and we will see conductance traces during this indentation and retraction, which will be something like this. And these conductance traces already reveal us the stable atomic configuration, the conductance of the stable atomic configuration. For instance, this is a remarkable one here, adjustable one G not here, here, and here. For instance, there is another one here as well. There are some smaller ones here and here. But if we really want to have a good statistics, then we have to do more than that. Let's say 10 to the 4 conductance traces like this. And we can make a histogram out of the conductance values which we get from these traces. So for silver, what we got for our sample was something like this, which has two remarkable features. That first of all, it has one single peak, which is the lowest peak in this histogram, which is usually defined to be the conductance of a single atom. And down, if the single atomic conductance breaks, then we only will have tunneling conductance, and due to the exponential cut of the tunneling conductance, we will see this divergence in the conductance. And in our case, this last peak was at a conductance value of 0.94 G knots, which is in good agreement with both earlier calculations and experiments. Just would like to have this paper for this. So if you want to make something similar for conductance switching, then let's see how can we do so. So let's go back to this experimental IV curve here. And what we want to have is that some sort of statistics on the conductance switching, which is the difference of the on-state and the off-state conductance. And what we really want to have is that some sort of statistics down to 1 G naught for the conductance switching, which means that for the on-state and off-state conductance, we really want to have no more than 10 G naught of conductance. Otherwise, we obviously won't really see conductance switching in the range of 1 G naught. So this means that for the resistance of the contacts, we do not really have lower than 1 kilo, let's say. So what we found in such case is that if we made 10 to the 3 distinguished IV curves, these IV curves are really different realization, meaning that we put the tip on the sample, measure the IV curve after we retracted it, and put it to another random place. So it's really good statistics in that sense that it averages over the surface. So what we found in such a case is that is a conductance switching histogram, something like this. So here we have the conductance switching value at delta G, and here we have the counts. And And for this histogram, what we have is that we can identify these two peaks, which is here we provided simply Gaussian fitting for these two peaks. And the first peak is at around 1.02 G0, and the second one is rather larger, it's 2.4 G0. And the main point is that this first peak here is really in good correspondence to a single atomic conductance for our push-pull histogram, which means that this conductance value and this conductance value is really in good coincidence. Although, apart from this, we really see some remarkable differences of the two histograms. So, for instance, this 1 G0 peak here on the conductance switching histogram is way broader than the 1 G0 peak here in the push-pull histogram, which can be attributed to less defined geometry. I mean, for indentation and the retraction, we really crash the surface of the silver layer, so that we really see a good metallic conductance always. While for this conductance switching histogram, we just really touch the surface. We do not really crash it through. And also, due to this surface contamination, it can happen that there are diffusive backscattering, diffusive interference effects, which can cause this conductance peak to be broader than this peak here in the push-pull histogram. But anyhow, the main point is that here we do not really have, we don't have this tunneling contribution. So for the push-pull histogram, we really see a tunneling contribution that if there is no breach anymore which connects to the peak to the sample, then we really see some conductance here, while we don't see any conductance at 0 G0. So there is no divergence here and virtually no values here, which means that there is indeed a minimum switching for this surface, which is just around 1 G0, corresponding to this single atomic peak here in the push-pull histogram, which leads us to the clue that we really have there is a huge role of silver atomic migration for this switching effect. Okay, and for this I would like to conclude my talk. So the main point was that we were able to make a switching configuration with plain silver surface with uncented in our point contact setup, both for low and high conductance values. And for low conductance regime, we see a switching conductance of 1 G0. Okay, and with this conclusion, I would like to thank you for your attention, and hopefully there is plenty of time for questions.
Time for questions. Yes.
So were you able to control for the contamination of the silver sulfide? Like, could you reproduce the results if there was?
No, not yet. So this will lead us to so this is a activity for further work. So this is not really controlled at the moment.
And then there's just one more further question. To get a conductance, you get the quantized conductance that you saw. Doesn't that mean you're traveling through a single state? Or I'm just a little confused what that would mean. So you see it in terms of G0, which is calling the quantized conductance. That means that's sort of the quantized conductance through a single channel, right?
Yes.
No, that's not true.
Well, I mean, not necessarily. But for silver, this is the case. So let's go to this formula, shall we? So, so here we have this formula, and this contains the sum of transmission values over I, which is the number of the transmission values. And for silver, and in fact all of the noble metals, it turns out that we had one single channel, and the conductance almost completely. But I mean, this is not necessarily the case. So it can happen that we have 100 tunneling channels, each of them contributing 0.01, which will lead us to the same conductance value. But for silver itself, I mean, this data does not reveal that what is the distribution of these PI values, but with other experiments and molecular dynamic calculations show that for silver, one has one single conducting channel.
But this in no way incorporates the sulfur.
Yes.
And so if you had no sulfur there at all, it wouldn't switch.
Because
I mean, it's not necessarily the case again, so I cannot really tell for this low conductance value whether sulfur plays any role or not.
because if you go back to the hysteresis that way, what frequency go back to the hysteresis curve we were showing?
This one?
So yeah, you have one ball there, and you have lots of heating. So you may have actually a motion of atoms because of heating.
Indeed, this major thing.
Even if you pull the sample before
Yeah, but I mean, heating itself is not necessarily enough because this is clearly an asymmetric curve.
Sorry?
So heating, I think, is not necessarily enough by itself because this is an asymmetric curve. So if it's only attributed to heating, then it should be symmetric.
Sure, but it is something that you may actually consider because heating, especially of one ball, is substantial.
Yeah, this can
Point context,
yes, I mean, in point contact that, yes. Although there is another thing that if the contact size is really substantially smaller than the inelastic mean free path, then the Joule heating doesn't contribute that much. Because Joule heating, you get Joule heating in the size range of the inelastic mean free path.
That's not true. It's the current density that counts. You have a
No, but you don't really have a Joule heating anymore if you have a contact size that's smaller than the inelastic mean free path.
No, it's not true. It's the current density counts. You have very few atoms, so you drive a large current in a very small area. So the number of scattering events per unit time and unit volume is enormous. In fact, people have shown that in a point context, you can reach thousands of degrees and burn them if there is not enough heating dissipation into the ball.
Yeah, but that's another contribution. I mean, there are other contributions such as electronic mean force and stuff like that, but it's not necessarily Joule heating. This is my point.
Let me follow on the sulfur question. Why do you think there's no sulfur on your tungsten tip that you started with? Because it seems to have a relatively uniform data set, which means either the whole damn surface of silicon go to sulfur, or you've got sulfur on your tip.
No, I mean, first, so what we usually do is to indent the tip really much so that we essentially what we will get rid of the surface contamination.
Well, if you do that, then you shouldn't have IV either.
That, I mean, so if we indent the tip at some place and we remove the tip and put it back to the surface at another place, then it will still contain sulfur.
I'm sure that there's more than, I don't know how you make it, but sulfuric acid plays a role. I'm sure there's more of this easy diffusion of any sulfur on the tip itself. Maybe.
Yeah, that can happen.
Yes.
And it works better.
You say you tackle the sulfur by ICAM?
It was Rutherford that's happening.
I'm sorry, which?
Rutherford that's happening.
Okay. I was just wondering what the sensitivity of it, how much sulfur you have.
Well, that's a good question. This is why I just told that maybe I just at least wanted to tell you that Auger electron would be better tool for this.
Before or after?
I think after measurements.
Yeah.
The honest curve remind me more on what is the oxide than what the diffusion on the silver structure. Because on satellite stuff, for example, the jump is much more pronounced than your curve. And this is exactly what we see for oxide. So are you sure that you're not switching the tungsten chip?
Or you've oxidized the silver.
Well, I mean, silver is more likely to contaminate by sulfur. This is what I surely know. And tungsten tip is not really likely to oxidize that much. What does it?
Tungsten is oxidized very Do you see this kind of stuff? Did you put tungsten top on the oxide material or you can have this?
Although we always start our measurement by cleaning with invention the tungsten tip, but I mean, still can be some stuff.
Let's thank our speaker. The last presentation of today. conducting a coupled order parameter model for resistive switching. What I'm going to talk about, if I wake up the computer, is very much work in progress. I want glasses too. It's not just me out of focus. So this is work in progress that I'm doing with Martin Miller at ICTP and Gary Zimmerman here at UC Davis. And one of the fun things about this is not just the collaboration, but the fact that, in a sense, this is what led to this workshop. And it's been a delight to have so many wonderful people come here and talk about this area. I think it's very exciting and very rewarding. So, of course, everybody knows about the background. I don't need to dwell too much about that. We just want to, for the purpose of this talk, but I'm sorry, the little black button? Oh, the big black button. We've heard many examples today of resistive switching. I just want to point out, typically the high resistance state is non-metallic. There is some sort of hoppy conduction, sometimes with variable range hopping. And the low resistance state can be metallic, optical, or non-metallic. And there are just some different examples here of PCMO or nickel oxide resistive switching. So what we were thinking about is, we've heard various models, certainly very wonderful talk this morning by Stan William and Chua about how to describe these memristors or switching devices. But we were thinking about having a model that is described by an order parameter that describes local order or a state variable. And for example, it could be your electric order parameter. That is, you have a local rearrangement or local ordering of the ions or vacancies also as a result of the switching mechanism. So, loosely speaking, in a locally disordered state, which is called P is equal to 0, you have high resistance, and you can have locally ordered states that have low resistance. And I just want to point out that in this case we have 3 states of the order parameter that we deal with: 0, the disorder, and plus minus 1, which are locally ordered. So then we will associate with the order parameter a free energy surface. And as I said, we will put the mean at 0 plus minus 1. And what we wanted to do is to couple this with a microscopic or coarse-grained microscopic description of the conductance. So really what we're thinking of, if you have a disordered system and you start to locally order it, you are really messing with the hopping or the overlap matrix elements between localized states. And so we have a coupling to the matrix elements or hopping parameters, which must then be either in the magnitude of p or p squared, because both p's plus 1 and 1 plus 1 are highly conductive or low resistance state. Then also we can have a coupling to the activation energy needed for a hop, depending on if the low resistance state is disordered metallic activation or activation. I just want to note, though, in addition to many of the talks and works I mentioned earlier today, Polstead and I, et al., and Schimel and Polstead, were using similar ideas, but they had a ferroelectric order parameter that essentially is p plus minus 1. So what I'm going to do now is just basically describe some ideas. As I said, this is work in progress, so I'm not going to pretend that we have a very nice finalized result. But this is just an example then of the free energy surface. Note that we have the usual, in this case, squared, quartic, and 6 order terms, and then we're adding, because they're allowed by symmetry, a term that couples the electric field E to P, and then a term in E times P squared. So the idea is basically, as I increase the local electric field, I can go from the locally disordered minimum
down to the position to be locally ordered minimum and -1, and then switch back and forth. And I just noticed also that the third order term here, as I said, which is allowed by symmetry, makes it easier to construct a free-energy surface that make these transitions allow. Then the next thing is to couple this to transport, and this is basically taken out of Markov Davis, where if you have a disordered systems, the conductance, apart from all these terms, the hopping range, the density states, and thermal activation, all that stuff, phonon frequency, like some characteristic frequency, you have the exponential overlap between the localized states, and you have an activation energy. And when the electric field starts to be appreciable, you also have the singe term in how much energy you gain in a typical optical range R. And then what we do now is we couple the exponential decay of the wave function to the order parameter, that should be P in the normal. And also we can couple the activation energy to the order parameter. And based on the free energy surface we can then switch between these minima. And as I said, I'm just going to give some examples of this. The kind of conduction J versus D that you can generate. These are just different values of disorder or activation energy. One thing I do want to point out also is that what this model actually describes is what the Hollander red curve is. So I go from low resistance to high resistance. Let's say I go back. Here I deliberately make the model asymmetric in the sense that I switch from high resistance to low resistance. But if I have, typically in an experiment, once you switch back to low resistance state, you do not continue to increase the magnitude of the voltage on the negative axis, but you continue to speed back up again. What this model does is it allows you to observe a re-entrance to a low resistance state as you continue, and then go back up here. Next, so summary, very simple order parameter, which is coupled to the local conduction mechanism, and we have just if you have sort of a neat field flavor for the kind of phenomena that this model can describe. And what we're working on now are essentially two different paths. One is to correlate this with a microscopic toy model, and also from the other end, work on 3D non-mean field simulations, including this model. And with that, thank you so much for your attention.
A lot of time for questions. See, I may not have used the correctly, but the mean field is symmetric, which means that whether it's a plus or a minus pi, it doesn't make any darn difference. How do you get bipolar switching?
Well, because you have the three element here, right? The whole point is that I'm going to switch from the locally disordered to one that is locally ordered with high resistance. But I can't switch directly from here to here. I always have to go through the intermediate state. And this is how you get bipolar switching by going back.
You identified a specific state. What's the actual physical reality of that state? It's not clarified.
No, it's not clarified here. I was deliberately vague about this. P, it could be actually really described in local atomic ordering. You know, for example, when you have irregular current channels in these devices, and as you increase the current density, you can have some local reordering of vacancies or defects in the system. That can be one thing, or it could be actual ferroelectric polarization. Generically, it's a state statement.
Other questions? Oh, sorry. Yeah.
Well, fundamentally, this is a thermodynamic model.
Yes.
And you're looking at essentially strictly bipolar switching from one side to another. The issue is that at least I think in practically all the switches that people are looking at, it's a dynamic system, and the range of states is continuous. So are you going to try to go from this sort of discrete type of model to a system that is continuous and dynamics?
Yes, that's right. So the next thing is you can then, with the free energy surface, you can define the kind of interlock view, which describes the dynamics of the different. So that's I didn't mention that in the future work, but the graphs are different.
Yeah, go ahead.
So, scale you was talking when you were talking about small features of the So I'm curious, how do you resolve this order parameter model, that the idea is that small localized systems where order parameters typically describe the system?
Well, so for a second, in all the different systems we've heard of today published, there are many different models and ideas and also experimental evidence for inhomogeneous or homogeneous conductors. That is, what is the resistance versus area state. So it's obviously easier to have a model like this if I assume that the conductance is not carried through local filaments. That can be described as something that is homogeneous or dynamic. And I don't particularly care if it's the last half nanometer or 1 nanometer or 2 nanometers. I have to be a little bit more careful if I'm trying to describe something which is where the low resistance state and the switching happens in very localized filaments. And I think a little bit more carefully it's hard to make a mean field theory obviously describes the bulk of the system, and I have to think in terms of localized regions where it makes sense for me to use.
Let me follow on. I mean, in the limit where we're talking about, sub-nanometer environment, we're talking about 1 or 2 or 3 or 5 atoms. How can you create mean field of 1 or 2 or 3 or 5 atoms?
Well,
Where one vacancy can totally switch, to a 3-atom environment.
I think so long as I have a few atoms, I can do that. So that's essentially my short answer to the question. And there is some local structure, some local group, whether it's on a half or 1 or 2 nanometer scale, that describes the switching. Related to these two, and I mentioned this earlier, on something that I found was very intriguing, when we made nickel oxide elements down to, I think, about 10 nanometers thick, and we measured them, and they showed beautiful, perfect, variable range hopping. To the 1 or 2, 1 to the 4 exponent. Now, and so the analogy I want to bring up is how can you observe variable range hopping in 10 nanometers? When actually the hopping distance itself can be several nanometers. How can you actually then make the choice of hopping ranges within that short distances?
Well,
I don't know. It puzzled me. It was very intriguing.
other discussion? If not, let's thank our speaker.
And one possible suggestion is that you try to stick around roughly this broader area. We will stage a lookout for the bus. When the bus will be here, we will announce it loudly. If you miss the bus, however, the hotel is a 15-minute walk, so you will make it. It's on the corner of B and First. Well, with this, today's session is closed. Tomorrow at 8:30, the bus picks you up at the same place, and tomorrow we will have a conference dinner. Thank you.
What was it? Oh.